Hello everyone and welcome to a new lecture about AI. Now that we have explored simulated annealing, we learned that simulated annealing is inspired by metallurgy and thermal process. So it's the time to move on to another powerful nature-inspired optimization technique, which is known as genetic algorithm. Genetic algorithm, also we call it as GA, these take their inspiration directly from biological evolution and natural selection. Just as living organisms adapt to their environment over generations, the genetic algorithm, evolve candidate solutions to optimize problems until they reach high-quality results. What makes them especially interesting in their ability to work on complex, high-dimensional, and nonlinear problems where traditional methods often struggle, they operate through a population of potential solutions which undergo process resembling selection, crossover, and mutation, just like in biology. In this lecture, we will examine how genetic algorithms are structured, the operators that drive their evolution, and how they can be applied to real-world optimization problems. So as we transition into genetic algorithm, it's useful to remember the principle that inspired them. Charles Darwin emphasized that survival is not about being the strongest or the smartest, but about being the most adaptable to the changes. The idea lies at the very heart of the genetic algorithm. Just like species that adapt to changing environments through evolution, the genetic algorithm adapts candidate solutions through process of selection, crossover, and mutation. Over successive generations, solutions become feeder and more capable of solving complex problems. So, this quote from Charles Darwin perfectly captures the spirit of genetic algorithm. What is that? Adaptation through variation and survival of the fittest. To illustrate the basic idea of genetic algorithm, let's consider a simple story. Imagine a king who wants to have more intelligent people in his territory. His reasoning is straightforward. If he brings together the best individuals, the next generation will also be strong and intelligent. In other words, the better input, the better output. We can map this story into the formulation of genetic algorithm. The population is the king's territory. Each individual in the population has a function, right? And this function is, in this case, whether they are intelligent or not. The king then selects the more intelligent people to what? To reproduce. And from their combination, new children or new solutions are proliferated. This analogy captures the essence of how genetic algorithm works by continuously selecting and combining the better ones generation after generation. Why? To improve their overall population. To understand the foundation of genetic algorithm, we need to look at their biological inspiration. In biology, cells are the building blocks of all living organisms. Inside cell, we have chromosomes, and they carry the hereditary information. Each chromosome is made of DNA, and DNA itself is composed of smaller units that we call them as genes. Genes are the fundamental unit that determine the characteristics and traits. So a chromosome represents a candidate solution, and instead of DNA bases, we usually encode it as a string of numbers like zeros and ones. Each position in this string is like a gene. They contribute to the overall characteristics, quality, or the solution. So this biological analogy is the core of genetic algorithm. Just as nature evolves better organisms through genetic variations, our algorithm evolves better solutions through encoded chromosomes. Now, let's connect the biological inspiration to the world of optimization problems. In many real-world cases, especially for NP-hard problems like the knapsack problem, scheduling, or traveling salesman problem, finding the exact optimal solution is extremely difficult. Instead, what we aim for is a near-optimal solution. What is that? One that is good enough and found within reasonable time. So this is where genetic algorithms come into play. Genetic algorithms, are directly inspired by natural evolution. They use mechanisms such as selection, crossover, and mutation to evolve solutions over generations. Formally, genetic algorithm is a type of evolutionary algorithm, or EA in short. These algorithms borrow the concept from biology, like inheritance and variation, and their aim is to improve solutions. Here is how it works. We first encode the problem input into a population of possible solutions. Each solution is evaluated by a fitness function, and this fitness function is used to measure how good it is. Then the algorithm iteratively selects the best candidate, and it applies crossover and mutation and generates new solutions. The cycle continues until the algorithm either reaches a desired level of quality, practical solution, or a termination condition, such as running for a set number of generations. So the genetic algorithm is so powerful, and what makes genetic algorithms so powerful is their ability to provide strong, practical solutions to problems that are otherwise intractable using classical optimization methods. So two important elements are required for any problem before a genetic algorithm can be used for a solution. One, method for representing a solution, like a string of bits, numbers, characters, like the termination total weight. Then the second one is method for measuring the quality of any proposed solution using fitness function. So here is the flowchart of the genetic algorithm. The process begins with initialization, and in here we have a set of individuals which are called as a population. Each individual is a solution to the problem that we want to solve. An individual is characterized by a set of parameters like variables, and we call them as genes. So genes are joined into a string to form a chromosome or solution. So variables are genes. Then a string of these variables, right, or we call them as chromosome, that is a solution to our problem, right? Then the set of genes are presented in binary values like 0 and 1, and we call them allele, right? Then we have a fitness function or fitness assignment. The fitness function determines how fit an individual is. For example, the ability of an individual to compete with the other individual. Fitness assignment gives a fitness score to each individual. The probability that an individual will be selected for reproduction is based on the fitness score. The next step is a selection. The idea of selection phase is to select the fittest individual and let them pass their genes to their next generation. Two pairs of individual or parents are selected based on their fitness score. Individuals with high fitness have more chance to be selected for reproduction. The next step is crossover. This is the most significant phase of genetic algorithm. For each pair of parents to be mated, a crossover point is chosen randomly from the genes. Offsprings are created by exchanging the genes of parents among themselves until the crossover point is reached. The next step is mutation. In certain new offspring forms, some of their genes can be subjected to a mutation with a low random probability. This implies that some of the bits in the bit string can be flipped. Mutation occurs to maintain diversity within the population and prevent premature convergence. Finally, we have termination. The genetic algorithm terminates if the population has converged. It means we do not produce offspring which are significantly different from the previous generation. Then it is said that the genetic algorithm has provided a set of solutions to the problem. Let's look at the classic example that we use to demonstrate genetic algorithm that is known as Knapsack problem. We are given a set of items that you can see here, and each item has two properties, weight and value. The challenge is to decide which item to include in our knapsack so that the total weight does not exceed a given limit, for example, 13 kilo or 50 kilo, while at the same time we try to maximize the total value. For example, in this table, we can see 6 items, and each item has a weight and value. So items are A, B, C, D, E, F, and they have some own weight and value. Our knapsack has a maximum capacity of 30 kilo, and the question is, which combination of items give us the highest value without breaking the weight constraint? It means the maximum constraint should be there. This is a perfect problem for genetic algorithms because it is combinational and NP-hard problem. Trying all possible combinations quickly becomes infeasible as the number of items increases. Instead, genetic algorithms allow us to evolve high-quality solutions by encoding each item choice as a gene, like 0 and 1. 0 for not including this item and 1 for including the item. Through selection, crossover, and mutation, we can find combinations that come very close to the optimal solution without exhaustively checking every possibility. Now that we understood the knapsack problem, let's see how it is represented in genetic algorithm. The first step is initialization. Here, each possible solution is represented as a chromosome, right? So the total solution is called as a population. Then each solution is called as a chromosome. So this is 1 chromosome, this is 2 chromosomes, 3 chromosomes, 4 chromosomes. And each chromosome has a gene, and the value of gene is 0 or 1. So 1, it means we include this item into solution. 0, it means we exclude it. For example, in chromosome number 1 that you can see here, 1, 0, 0, 1, 1, 0, right? It means the item number 1 will be there, 2, no, 3, no, 4, 1, yes, 5, yes, and 6, no. So then we have a collection of chromosomes that we call them as population. The algorithm will evolve this population across generation. And what is the objective? To find better and better solution. This step set the stage for evolutionary phase. By encoding solution in this way, genetic algorithm can apply operators like selection, crossover, and mutation to systematically explore the search space. So in here, we're gonna calculate the fitness assignment. Fitness assignment, it means we have some chromosome, right? Chromosome 1, chromosome 2, and the rest, right? Chromosome 1, it means item A should be there, B no, C no, D should be there, E should be there, and F should not be there. Then we calculate what is the weight. 15, 5, 9, 29 is the weight of this chromosome, and the value is 28. For the second one, A and B is not there, C is there, D is there, E is there. We calculate weight and value. We do the same thing for the other as well. So the chromosome with the highest value is selected. So it means here this value is 28 and this value is 23. So this one is the best one. We do the same for the other as well. So now let's look at the selection step. This is a crucial part of the genetic algorithm process. Selection determines which individuals from the current population will be chosen to create offspring for the next generation. There are several common methods, including roulette wheel selection method, tournament selection, rank selection, and elitism selection. So in the roulette wheel selection method, individuals are selected based on their fitness proportion. Think of it like a weighted lottery where fitter individuals have a higher chance. Then we have tournament selection. Here we have a group of individuals and the fittest among them is selected. This introduces controlled competition. Then we have rank selection. In here, individuals are ranked based on fitness and selection probabilities are assigned according to rank. And in this way, we can reduce the chance of premature convergence. And the last but not least is elitism. So in here, the best performing solutions are carried over the next generation, and we want to make sure that optimal solutions are not lost. So among them, we go roulette wheel selection methods. So after calculating the selection probabilities, the next step is to select parent for the next generation. In this roulette wheel selection method, we imagine a wheel that the wheel is divided into some solution, and each chromosome occupies a portion proportional to its fitness value. Then we spin the wheel and the chromosome in front of a fixed pointer is selected as a parent. And the probability is Fi for each one divided by sum of all, right? So maybe we divide into M sections and M is the number of chromosomes. So then, each chromosome has a value and it has a percentage, right? So we rotate the wheel and the section stops in front of the fixed point that is selected as the parent. This method ensures that chromosomes with higher fitness have a higher chance, right? Because this one has 28.9% chance of selection, this one 23, and this one the highest, right? 35. More space is assigned to chromosome number 4. So in here, chromosomes with higher fitness have a higher chance of being selected, but it still allows less fit chromosome a chance, and in this way, we can maintain diversity in the population. We found the parent chromosome in the previous step. The next step is crossover. For each pair of parents to be mated, a crossover point is chosen at random from their genes. In the crossover step, selected parents combine their genetic material to produce offspring. This process mimics biological reproduction, and this is central to generating new solutions in this algorithm. So there are several common ways. One is 1-point crossover, 2-point crossover, and uniform crossover. In the 1-point crossover, in here, a single cut point is chosen and segments of the parents are swapped. In the 2-point crossover, we use 2 cut points for exchanging segments. And in the uniform, the genes are exchanged randomly according to a fixed probability. So this process of crossover introduces diversity into the population by preserving useful traits from their parents, and this can help the algorithm to explore new potential solutions in an effective way. So here is the crossover. As I said, we have 1-point crossover, multi-point crossover, or 2-point crossover, and uniform crossover, right? So in a 1-point crossover, a single crossover point is randomly selected, like here, right? Then the gene material bits are exchanged after this point, right? So you can see here, this is one parent, this is one parent, these are crossover. So you can see here, this 101 is the same, but instead of 0, we have 1 here. So 1 is the same, and instead of 1, we have 0 here, right? In this case, we only change these 2, right? So 1, 0 is the same. This was 0, 1 came from here, and 1 same. But in here, uniformly we change, right? So 1, 0, 1, 0, 1, 1. So 1 is from here. This one is from here, 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 and the rest, right? But 0 is from here. So this is called as uniform crossover. We now come to mutation. This is the final step in generating our new population, and this is essential for evolutionary success. Simply put, mutation is a small random change in the genes of new offspring. So as you can see here in this example, a single bit in the binary string is randomly flipped. So it was 1, it has been changed to 0. The fundamental purpose of mutation is to maintain population diversity. Crossover is great at combining existing successful traits, but it cannot introduce entirely new ones. So mutation is our tool for exploring uncharted regions of the search space. And this mutation helps us to escape local optima, those good but not best solutions where the population might otherwise get stuck. We apply mutation with a very low probability that you can see here, that is Pm is equal to 1 by L, and this L is the chromosome length. So we can call this mutation as the random explorer, and this guarantees that the search remains robust and capable of finding truly novel solutions. We have now generated our new offspring. The final step is replacement and evaluation. First, we evaluate the fitness of all new offspring to determine their quality. Then we must decide how to replace weaker individual in the current population with these feeder offspring. We use several strategies like generational replacement, steady state, and elitism. In the generational replacement, we replace the entire parent population with the new offspring. In steady state, we replace only a small number of the weakest individual. And then a critical addition is elitism, which ensures that the single best chromosome found so far is always carried over the next generation. And in this way, we can prevent from losing the best solution we have discovered. So these strategies complete the cycle of the genetic algorithm, and they give us the new population ready for the next round of evaluation. So finally, the question is when to terminate. When do we need to stop the genetic algorithm? There are typically three main stopping criteria. One is no improvement. The algorithm stops if there is no improvement in the fitness of the best individual for a set of consecutive generations. If evolution stagnates, continuing the search is likely inefficient. The second one is predetermined generation. We count them, right? So this is a simple one. And when we reach a predetermined number of generation, we stop. For example, we just stop after, say, 100 or 1,000 generation, regardless of the quality of the solution. And the next one is predetermined value. The algorithm halts if the fitness function achieves a predetermined value. This is used when we know the optimal solution value, and simply we stop at the moment we find a chromosome, that chromosome reaches or exceeds that target score. Once any of these conditions are met, the algorithm will stop and the best individual found is presented as the solution. All right, so let's go back to our problem. We want to find the best solution, right? So our algorithm starts by generating random chromosome, right? For example, we have 0, 1, 1, 1, 0, 0. This is one solution, right? Another solution can be, for example, 1, 0, 0, 0, 1, 1, right? The next one can be anything, right? So we may generate 100 chromosomes, and each one is, for example, A should not be included, B should be there, C should be there, D should be there, E and F are not there. Then we go for fitness evaluation. For each chromosome, we find out the total weight, right? So total weight is equal to sum of weights multiply genes, right? We calculate for each one. And always we take care that weight should not be more than 50, for example, if the maximum capacity is 50. For example, if our chromosome is 1, 1, 1, 0, 1, and 1, the weight is, for example, 49 kilo, and the value is 57, right? This is high fitness. If, for example, we select one from each one, right, then the weight will be 54, and this is not possible because this is more than what we can have, right? In the next step, we go for selection based on roulette or fitness proportionate. Chromosomes are selected based on their fitness probability. High value combination, for example, including A, B, C, E, F, these are more likely to reproduce, and poor or infeasible solutions are gradually removed from the population. The next step is crossover. The pairs of selected chromosomes undergo one-point crossover. For example, this crossover mixes genes from a strong individual, and we create offspring that combines good traits. For example, we have selected two solutions as 1, 1, 1, 0, 0, 1, and another one as 1, 0, 1, 0, 1, 1, right? After one-point crossover, just we change these two, and we get that the best solution is 1, 1, 1, 0, 1, and 1, right? This 0 has been changed to 1, right? Then we go for random small flip with, for example, 1% to introduce diversity. So, for example, if our chromosome or our solution is 1, 1, 0, 0, 1, 1, we may change one of them, this one, to 1, right? For this one, we cannot change because it will go more than the capacity that we have. In the next step, we go for replacement and evolution. In here, the new offspring replace the old generation, and fitness values are recalculated. After several generations, like 10 to 15 generations, the population converges toward the best chromosome. Finally, through repeated selection, crossover, and the mutation that we discussed already, we will go for high fitness chromosomes, and we will select that one. And for example, after changing all these things, we came up with this solution as the best one, right? So in this case, we will calculate what do we had. For example, the weight is 15 plus 3 plus 2 plus 9 plus 20 is equal to 49, and the value is 15 plus 7 plus 10 plus 8 plus 17 as 57, right? So this is still under 50 kilo possibility that we had, and the value is 57, right? So after this one, we have no other feasible chromosome that achieve a higher total value, which is less than 50. So this is our optimal solution. So our algorithm found this solution by evolutionary improvement. We first started with initialization, random exploration. Then we go for selective reproduction of high-value solution that is called as selection. Then we go for crossover. We go for combination of promising features. Then we apply mutation, occasional random innovation, and finally we go for termination. We iterate improvement until convergence. Okay, so to conclude our discussion on genetic algorithm, let's look at where they are successfully applied. Genetic algorithms excel at complex optimization and search problems where the solution space is vast. They are widely used in knapsack problem or deciding which items to pack to maximize value while respecting weight constraints. For example, you want to buy a ticket and you want to include different kind of options in your ticket, but you want to minimize the price. The second one is scheduling and timetabling, creating optimized schedule for airline, universities, or manufacturing plants. The next one is VLSI and circuit design, finding optimal layouts for integrated circuits. More recently, the genetic algorithm become critical in machine learning, like neural architecture search for designing the structure of neural networks, for feature selection in machine learning, choosing the most relevant data inputs for a model, and hyperparameter tuning that automatically finding the best setting for a learning algorithm. And also many other domains, genetic algorithms are powerful tools for tackling problems that are too difficult for traditional methods. Thank you very much for watching this video lecture. Please feel free to ask me your questions. Thank you and see you in the next lecture.